So this is my first NMI event. It's a pleasure to be here and to meet you all. As mentioned, I'll be talking about system technology optimization. That's my role at IMEC. I'll try and give a brief overview of IMEC for those who don't know us. And even those who know us, I'm sure don't know everything we have. So I'll give that a shot. Okay, here's the overview. So IMEC is a non-profit R&D lab, so mostly in Belgium and the Netherlands. There's a photo there of our site in Leuven with fabs. These are R&D fabs, although we do some low-volume manufacturing of MEMS devices or custom imagers and that kind of thing, largely in our 200mm fab, I believe. The 300mm fab, we have EUV machines, so absolute bleeding edge there, looking at half a nanometer CMOS sort of capabilities as a research demonstrator capability. Now, notionally 5,500 employees. I haven't seen an exact breakdown of this, so maybe take that with a little bit of salt. That includes all of the assignees from our partners. It includes all of our PhDs and part-time professors. But there's at least 2,000-3,000 employees at IMEC. Not quite that many in the UK yet, but we'll get to that in a second. Other thing to note here is that we're 75% industry funded. We have government funding, schemes, projects, structural funding, but actually most of the work we do is funded by industry. And my program, which I'll be talking about mostly, is an industrial membership program. Okay, so how does it work? So as I said, we are doing pre-competitive research for industry. So it has to be industrially relevant, but we work a lot with academia to sort of channelize their innovations and to steer them towards problems that we see as industrially relevant. We work with a lot of equipment suppliers. So ASML's name came up earlier, very key partner, but we work with everyone in the supplier space, materials suppliers as well as equipment vendors. And I saw an announcement this week that we have just launched our joint lab with ASML on high NA EUV, so absolutely enormous machines there for doing that kind of super high resolution lithography. And we do startups as well. So I think it was on the previous slide, maybe 100 odd startups that IMEC has done, and there's some VC activity as well. Business models. So we collaborate very proactively. I'm in the R&D organization on the technology side. My colleague Steve is here. Some of you may know he formerly led the sort of the big services business that you may have used if you've used Europractice or IC-Link. As it's known, and then venturing startups. So this is my last marketing slide, I promise, but this shows you the sort of range of stuff we have at IMEC, right? We're best known for technology maybe, but we have platforms on top of that. We have systems and SoC architectures. We have applications as well. So we have smart city and smart agriculture. We have implantable brain probes that are manufactured with MEMS processes. And so this makes it really hard for me as UK site lead to actually represent the whole range of IMEC's interests, but I do my best. And if there's some specific angle you're interested in, hopefully I can hook you up. So IMEC UK, all right, we're not thousands yet. There's 9 of us in the UK. We've been here for 2 years. I joined in August 2022. So we're designers. We're design focused. So we're trying to tap into the design talent in the UK. So I think I'm one of the few designers here, and maybe the only one on stage so far today. So I'm a circuit and system designer. I'm not a scientist, I'm not a physicist. We have projects in optical, we have projects in wireless, we have memory, computer architecture, but system technology optimization is our main value proposition here. So I'll tell you much more about that. We are working with academia already. I've got 2 co-funded, co-supervised PhDs. I've got budget for 20. I don't have supervision bandwidth for 20 yet, so I need to go to the team in order to make that happen. And we are looking to collaborate in other ways in the UK, whether that's funded projects or industry partnerships or whatever else. Okay, so the CMOS technology landscape, but through System Eyes. So there's a lot of interesting stuff happening in SoC products. Yeah. Apologies for no UK examples. Sometimes I use GraphCore in this slide, but you see a lot of innovation here, whether it's 3D stacked memory in CPU products like AMD, advanced packaging, heterogeneous technologies in the Intel case, or redefining where compute happens, like in the Samsung case, where you are pushing compute into a HBM DRAM stack in order to avoid some of the memory bandwidth and energy bottlenecks of moving data to compute, doing two operations, and then sending it all the way back. Yeah. So these innovations are painful. They are disruptions, but they're happening for good reasons. I'll come back to that in a minute. But NVIDIA came up earlier. So here's a graph from Bill Daly, who's the chief scientist at NVIDIA. And he shows a very impressive 1000x improvement in their AI inference performance on their GPUs over 10 years. 1000x in 10 years. And for all the process people in the room, he attributes only 8% of that to process. But when I looked at this in more detail, this is classical process scaling, right? He's talking about clock frequency. And we know there's a lot more to CMOS technology scaling than clock frequency now. Yeah. And in fact, all of the rest of it is enabled by transistor density. The hundreds of processing elements in these GPUs, they haven't gotten larger, but they have got more complicated. Yeah, they support a wider range of number formats, like 8-bit floating point, for example, which let you do more instructions per cycle and crank through more inferences per second. Yeah, and without CMOS density scaling, that can't happen because otherwise things get bigger. Okay, so what is the density roadmap? And this is an area where IMEC leads. This is the CMOS transistor roadmap that IMEC puts out, and you can see the progression there from planar transistors through FinFET devices, through nanosheets, which are coming next from 2 nanometer onwards, and then even beyond that to CFET devices where you have the NMOS on the PMOS or the other way around, for best packing density. And density scaling will continue. It's getting harder. It's getting more expensive. We're putting a lot of effort into it as an industry, but we see the scaling trend slowing down here. Yeah, so there's a knee in the curve. We're going to be seeing 20 to 30% transistor density improvements or gate density improvements per node, rather than 70 to 80% that we saw in the past. So that's one of our problems. Another problem, if we look at supercomputers, yeah, and I heard energy spoken about this morning. So if we look at supercomputers, because they are publicly funded and therefore publicly benchmarked, you can get good energy data. Yeah, so performance is exponentially increasing over time, and this is the number one supercomputer per year for 20 years. Performance is up, energy per operation is down. Good news until you look and see that the slopes are not matched. Yeah, so in 2030, we'll have 70 exaflops at 2 picojoule per operation. That's 140 megawatts per supercomputer. For one or two supercomputers, maybe it's okay, but the chips that go into these then go into data centers, and we can't afford to have 7 times higher power in our data centers in 2030, let alone the scaling beyond that. So actually, our ISO power energy target, needs to be improved by 10x or more. Yeah, that's 10x assuming very efficient software. If you look at other software benchmarks that show 10x lower throughput on the same hardware, then you need to deliver another 10x energy. So this is the problem that our industry should be working on, energy. Another barrier here is the availability of data. So again, back to Bill Daly, NVIDIA, absolutely massive, designing chips in 3 nanometer, 2 nanometer, shipping very high volume in 5 nanometer. But Bill Daly, oops, it's impossible to stop the progress of technology, of course, like my slides. So everybody references 45 nanometer energy data. Yeah, this is data from 2014. Academics do this when they propose new accelerators, new architectures. Even chief scientists at large companies do this. And so this is a gap, right? We know that 45 nanometer is not representative to today's products in advanced nodes. So IMEC there is trying to fill a gap, catch it while you can. We're putting out 2 nanometer data, nanosheet data based on IMEC's predictive process design kits that show what is the energy per operation and actually how much more does it cost for a 32-bit floating point operation these days than an 8-bit operation, and it seems to be relatively higher. Yeah, so if you design for 45 nanometer, you will be vastly suboptimal. Okay, one more time. So this will be published in September. The other good thing we're doing here is actually we're going to release this PDK for academia, for startups, for industry to work with and collaborate on and be able to exchange data without falling foul of Foundry NDAs or whatever else is the barrier currently. Okay, so that brings me to system technology optimization. Okay, this is a research program that I lead. And this builds on top of design technology optimization, which is a process that IMEC sort of trailblazed over the last 10 years. When you see TSMC or Intel now announce their new process, they don't talk about how small their SRAM bit cell is. They don't talk about how small their NAND gate is. They talk about the power, the performance, and the area for a CPU that they've ported. Yeah, that's what you show now. And it's because it's a co-design exercise. You don't just do the NAND gate and then hope that everything on top of it is better. You have to go up to the design, and then you have to fold back the feedback that this particular design rule is in the way of our density, or this particular high resistance metal is blocking us from achieving ISO performance with the last node. So that's very well established. STCO adds on top of that. And that's new and that's challenging. People tend not to get it, but hopefully I will fix that for you today. So what we need to consider is, a one-size-fits-all CMOS technology where you make it smaller, it gets faster, it gets lower power, it gets cheaper. That's not what we have today. Yeah, and so we need to consider, what does mobile need? What are their big challenges? What does cloud server need? How do we tailor technologies for them? What does edge need? We heard about augmented reality earlier. Yeah, there's a very challenging power and footprint and density challenge there. So to give an example, and I'll have 2 more later where we have specific results to show. A technologist, and you see this in academia all the time, so you may have seen this from your local university, will say, AI is big, I'm a magnetic materials person, is my magnetic memory beneficial for AI? That's a sort of bottom-up technology question. Whereas the system designers will be looking at the technology options, the memory options they have from the foundry, and saying, for this particular memory in my architecture, which of these memories should I choose? Massive gap there, right? So the STCO question sits in the middle, and looks outwards, looks upwards and downwards, and says, how do we co-design for 10x wearable AI efficiency? Yeah, technology is in scope, system is in scope. I can draw on both and really co-design the solution. And just to highlight the differences here between all of these things, because I guess we're not all systems designers here. So mobile, it needs to be small, it needs to be cheap. It's very heterogeneous. Yeah, you may have 3 different kinds of CPUs in there. You have a GPU. You'll have various accelerators for video, for audio, and whatever. So it's a very complicated and already specialized little system on chip. Whereas cloud servers, you might have 100 of the same CPU stamped out. Yeah, so they are, bizarrely, although they're bigger and they're higher power, they're much easier to model because of that homogeneity. Data GPUs, similarly, even more, hundreds of little processors in a GPU. And then wearables, a bit of a nascent market, but that needs to be highly accelerated for better performance, better efficiency, but also very form factor constrained. Disintegration of chips, big thing, big trend. We see this everywhere, but they will embrace it in different ways. So in cloud, for example, that's already been there for five or more years. It's cheaper if you deliver a number of compute chiplets with an I/O chip in an older technology, for example. AMD led the way there. In GPUs, I see this in things like Tesla's Dojo architecture, where they have 25 custom GPUs on a wafer scale package. Yeah, because they just want density, throughput density, beyond the reticle and beyond the technology limits. And power. My background is power and energy in digital systems. So this is really interesting, right? So everybody is power constrained, whether it's for thermal reasons or energy bills in the data center, or because batteries are improving at just 1% per year, whereas the length of a day for your mobile is still fixed. Anyway, so you can look at these and you can sort of map all of the technology options that we have, vast menu of technology options at IMEC and elsewhere, and say which of them are more relevant to which domains. And then, upon that, you might say, actually, I'm going to use 3D partitioning differently in each of these. So this is my job, to identify these pairings and then to evaluate what the benefits are and do the technology specs need to change. Okay. So how does STCO work and what does it get us? Okay, so thermal. Okay. So thermal. Thermal is a huge problem. So I said we're all power constrained. Now, in some cases, we're power constrained because we can't cool the devices anymore. Yeah. We're not at the power density of the sun, and I don't think we'll ever get to the power density of the sun, but it is a serious problem. Yeah. We are still delivering logic density, 20–30% per node, and we're not delivering voltage scaling anymore. If you're familiar with Moore's law, maybe the timescales are adjusted a bit, but we don't have Dennard's law anymore. We don't have Dennard scaling. Yeah, that ended 20 years ago. So now every time we deliver more density, we also increase power density. Power density increases temperatures, or in fact, decreases our performance to maintain the same temperature. Okay, so we do a lot of thermal research in IMEC, and here's a sort of an example of cross-stack approach here, where you sort of process on the bottom and workload on the top, and how we show them interacting. So if I go left to right, we are looking at an A14, so 14 angstrom nanosheet technology there, implementing an array of RISC-V CPUs, fully placed and routed using IMEC's internal PDK, and we compare it to a CFET technology, half an angstrom in this case. We pack in twice as many cores. Power per core goes down, but the overall power per fixed area goes up, and therefore, unless you do something more in the management, temperature also goes up. So that's what this figure on the left is showing, and this is from a publication that we have done. Now, that looks upwards, and you need to say, like I said, temperature can't go up, performance has to come down, and so then you need to look at the power management schemes that you put in place, so dynamic voltage and frequency scaling, DVFS, which allows you to sort of back off the performance, recover energy efficiency in a square term with voltage, and manage your temperature appropriately. And then if you look at whole SoC, so this is a large SoC that we modeled on the right. This is a cloud server chip with 80 CPUs. So you can then think about, okay, how do I map workloads on this kind of complex chip? Yeah, where do I put each of my customers' jobs with different relative powers in order to manage the overall system temperature? Yeah, so it gets pretty complicated. It's not just about the transistor. So then 3D. 3D is a hot topic, and thermal for 3D. Also a hot topic. So if I give you an example of what we're doing here, moving from right to left this time. So what I'm interested in here is actually, rather than take system architectures that exist today, fold half on top of the other half, and then ship that quick, I want to know longer term, what does a 3D native system look like? Yeah, how would I architect for 3D? And IMEC has some very advanced 3D capabilities. We've demonstrated 400 nanometer pitch hybrid bonding already. And so, how do I take advantage of that in the system? So you end up needing a very agile workflow here, where your technology parameters are an input. You regenerate an architecture based on those, but then you need to flow back to the software. And how do you map a workload onto that? What does that mean? And then we go to the left. And we look at, okay, how do I actually prototype that? How do I evaluate the power? And then you need EDA. Yeah, so we work with Cadence, and this is a publication that we did with Cadence to enable 3D place and route, so concurrent 3D design of 3 layers in this example where we have an L2 cache on top of an L1 cache on top of a logic die. So very important to collaborate on this kind of thing and to enable the ecosystem. Okay, so to conclude then, so IMEC is a semiconductor research institute, non-profit as I mentioned, growing presence in the UK, 9 people today, but I've seen slides projecting massive growth up to ideally 50 or 100 people, so we will be growing. CMOS logic density scaling continues, but there are a number of challenges like power efficiency, thermal, memory scaling as well that I didn't mention, but there's a number of large challenges there that we need system innovations to work around. So STCO that I lead, system technology co-optimization, it enriches the technology roadmaps. It allows them to avoid dead ends such as thermally uncoolable scenarios, and we will increasingly rely on STCO. Much as DTCO has become very mainstream and very key to foundry technology roadmaps over the last 10 years, STCO will be that in the next 10 years. And what we need are good designers there, and we need good cross-stack collaborations. So we need designers to get involved in technology, and that's why I'm here, and that's why we're here in the UK. So if you'd like to talk about collaboration, I'm around, Steve's around. Thank you very much.